Hi and welcome to Week 7 Mini Lecture 2 for Thermodynamics for Educators. This week we're going to look at the macroscopic definition of entropy and how we can use it to calculate the changes in entropy for various simple processes. Just a reminder of what we've been doing the past 3 or 4 weeks. We've figured out a microscopic definition of entropy. This is the Boltzmann definition of entropy in terms of the number of microstates for a particular macrostate. We've used this formula combined with our intuitive notions of what it means for a system to be in equilibrium with respect to heat flow or changes in volume or changes in particle number to derive the thermodynamic identity. From the thermodynamic identity, we'll see in the reading this week that we can obtain the definition of entropy as a small change in entropy to the system is caused by a small change in the heat added to the system divided by the temperature of the system. And this is valid for reversible processes, and this is valid for any reversible process that you encounter. This is the Clausius definition of entropy. This is the macroscopic definition in terms of macroscopic variables, heat and temperature. Now occasionally you will encounter this relation written in this way with a little bar across the differential sign in dq. What this is meant to emphasize is that heat, just like work, is not a function of state, but entropy and temperature, in fact, are. And that means that dq is not a differential in the strict mathematical sense. We don't need to worry about that too much here. The important thing to bear in mind, of course, is that things like entropy and temperature and the other thermodynamic variables we've encountered are functions of state except heat and work, which are not. The other thing I want to emphasize is that this relation is only true for reversible processes. It is true for any reversible process, but it is only true for reversible processes. And I'll remind you that reversible essentially means quasi-static. So it's processes that you do very, very slowly. You make infinitesimally small changes at a time. Real-life processes that occur in the real world are not reversible. They're not quasi-static. And for real-life processes, the change in entropy is always bigger than dq over t. So you might ask, well, what's the use of studying this, ds is dq over t, if this is not valid for any real-life processes? And I'll answer that question later on in this lecture. Now, let me cover some basic implications of this equation here. Suppose you have two objects, A and B. A is at a higher temperature, B is at a lower temperature. And suppose a certain quantity of heat flows from A to B. So this is delta Q, this quantity of heat. So the heat flow from A is minus delta Q because it's losing heat, and the heat flow into B is plus delta Q because it's gaining heat. But delta Q is the same. The heat lost by object A is the same in magnitude as the heat gained by object B. That's just conservation of energy. We can say that the flow of energy like this, the flow of heat, behaves like a conserved fluid. It's like water flowing from one place to another, down some pipes. If there were no holes in the pipes, then the amount of water leaving one area is equal to the amount of water arriving in another area. Indeed, historically, the original conception of heat was as a fluid. We know it isn't really a fluid, but mathematically it kind of behaves like one. But it is a conserved fluid. No heat. Heat isn't spontaneously created from out of nowhere, and energy isn't spontaneously created out of nowhere, nor is it spontaneously disappeared. Now, entropy is a little different. So you can ask, what's the change in entropy of object A and object B? Well, you just use this formula here. It's delta Q divided by the temperature of the object. Now, delta Q is the same for both objects in this formula, but T is not the same. T is higher for object A. That means delta S has to be lower because T is in the denominator down here. So higher T means smaller delta S. So object A loses some entropy, but the magnitude of that entropy is smaller than the entropy gained by object B. Object B is at a lower temperature, and a lower T in this formula means higher delta S. So object B gains more entropy than object A loses, which means that the net change in entropy is positive. And that's the second law of thermodynamics. In any process, the change in entropy is greater than or equal to 0. So entropy can also be treated as a fluid, but it's not conserved. Entropy can be created out of nowhere. And in fact, in all real life processes, entropy is created out of nowhere. There is a positive increase in the amount of entropy. Just as an aside, treating entropy as a fluid is not just a nice analogy, it is actually very useful in many practical applications. In my field of research, which studies neutron stars, we can model the interior of neutron stars as a fluid, and in fact, there are many papers which treat the entropy of that fluid as a fluid itself, as you can see in this abstract from an actual paper. So this is more than just a useful analogy, it is useful in practice as well. Okay, let's think about some of the most basic reversible processes that we've encountered. So you could have a process that occurs at constant volume, an isovolumetric process. So no work is being done on the system. In that case, dq, the heat flow, is equal to the change in the internal energy of the system, which is equal to the heat capacity at constant volume times dt. And in that case, ds is given by this formula here. Therefore, the total change in entropy during this process is the integral of this formula from the initial temperature to the final temperature. Well, if the heat capacity at constant volume is constant with respect to temperature, which to a good degree of approximation it is for, say, an ideal gas, then we're integrating 1 over T. And 1 over T integrates to the log of T. As an aside, some of you have been asking in the comment threads, why does the natural logarithm occur in nature as opposed to, say, logarithm to the base 10? Well, here's one example. The integral of 1 over a variable, the integral of 1 over x, is log of x. It emerges naturally out of the mathematics. And this logarithm occurs often in a variety of contexts in physics in the real world. So, in a sense, asking why the natural logarithm occurs in nature is kind of like asking, well, why does pi occur in nature and not any other number? Well, it does, because that's the way nature works. That's the way the mathematics works. So the change in entropy during a constant volume process is given by the heat capacity at constant volume times log of the final temperature minus log of the initial temperature, which using the property of logarithms can be written more simply in this form here. Now, you could instead have a process that occurs at constant pressure, in which case the heat flow is equal to the change in enthalpy, which is equal to the heat capacity at constant pressure times the change in temperature. In that case, the change in entropy is given by this formula here, which, as you see, is pretty much the same as this formula here, except we've got the heat capacity at constant pressure instead of at constant volume, and that just leads to a similar formula, again, with the different heat capacity there. So let's put these on a PV diagram just to give a bit of a visual on this. And for an isovolumetric process, we've seen delta S is given by this formula here. And for an isobaric process, a constant pressure process, delta S is given by this formula here. What other processes have we encountered that are reversible? Well, adiabatic processes occur with no heat exchange. Well, if no heat is exchanged, dq is 0, and that means delta S is 0. So an adiabatic process is actually an isoentropic process. It occurs with 0 exchange in entropy. So this is that rare case, that one allowable case in the second law of thermodynamics where instead of the change in entropy being greater than 0, it is equal to 0. That is only true for adiabatic reversible processes. Now be careful, because there are plenty of adiabatic processes that are not reversible, in which case the change in entropy is greater than 0 again. All of these processes that we're covering at the moment are assumed to be reversible. The final process that we've encountered is an isothermal process. So temperature is constant here, and therefore the total change in entropy is just equal to the total heat added to the system divided by the temperature of the system, which is unchanging during the process. Now, if you remember from this table that we encountered back in week 2, the heat flow into the system for an isothermal process is given by nkt times the logarithm of the final volume over the initial volume. So if we insert this into this formula here and cancel out the temperature, we get that the change in entropy is just nk times the logarithm of the final volume over the initial volume. We've actually already encountered this formula, and we've used it to prove that if a gas expands to twice its volume freely, without the temperature changing, then its entropy changes by a factor of nk log 2. So we can actually add all these results to this table here. Let's just stick in an additional row here for delta S for these 4 types of reversible process here. Again, this is a handy reference sheet for you to keep on hand when you're attacking various simple problems in thermodynamics. So we've kind of completed a full circle here, starting out at the beginning of the semester with some basic macroscopic thermodynamics, then descending into the microscopic world, which allowed us to derive the ideal gas equation of state and get at the statistics, the statistical origins of thermodynamics, which allowed us to derive entropy and derive temperature from microphysics, and then we've worked our way back up to the macroscopic level again, where we're reunited with all the things that we've done in the first 2 weeks of this class. Now, let's return to the question of why we're interested in reversible processes if all practical processes are irreversible. Well, it's because entropy is a state variable. In other words, if a system starts out in one state, let's represent it by a point up here on the PV diagram, and then some process happens which takes it to another state down here, then the entropy at the start and the entropy at the end for the system is the same no matter what the process is that takes you from the start to the end states. Now, real processes are irreversible. They happen by some route that we can't even really draw on the PV diagram because irreversible processes are not characterized by a single value of pressure and volume at any given time. But if we take a real-life process and we want to calculate the change in entropy, all we have to do is imagine traveling between the initial and final states by some combination of reversible processes. So for example, we might say to get from this bottom state here to the top state here, we might travel up an adiabatic path and then move along an isobaric path, in which case the change in entropy for this real world process is just equal to the change in entropy along the adiabatic route, which is 0, plus the change in entropy along the isobaric route, which again we can compute using the equations that we've just derived. So this is why it is useful to consider reversible processes. They actually allow us to calculate the changes in entropy during irreversible processes, i.e. real-world processes. Finally, I want to touch upon the third law of thermodynamics, which you'll read about as well in the book this week. So the change in entropy we've seen for a constant volume process, for example, is just the integral between the initial and final states, the initial and final temperatures, times the heat capacity at constant volume over temperature dt. Now imagine we start from absolute 0, so a temperature of 0 Kelvin. And S0 here is the entropy of the system at 0 Kelvin. Now, in the book, it's pointed out that we might run into a problem here, because if the temperature is 0, then 1 over T is equal to infinity. But we know that entropy is always finite. It's equal to the number of microstates for a macrostate, and that's always finite. So the only way out of this is that as temperature approaches 0, the heat capacity at constant volume has to approach 0 as well, and 0 divided by 0 cancels out and gives you a finite answer. This is probably the best way of stating the third law of thermodynamics. It states that the heat capacity of any substance must tend to 0 as the temperature tends to 0. Now, for an ideal gas, the heat capacity is constant. So the third law tells us that the heat capacity for a gas must stop being constant as you get to very low temperatures. It must start decreasing towards 0. In fact, for a solid, the heat capacity is given by some constant times temperature plus some other constant times temperature cubed. But that's okay. If we know how the heat capacity depends on temperature, we can still compute entropies. In one of the problems of the homework, you're actually asked to do this for this form of the heat capacity. You just plug this into this equation here, you cancel the bottom t with one of the top t's, and then you integrate this equation here. Apologies, this bottom t in the denominator on the right-hand side here shouldn't be there. This is just a plus b t squared dt that we're integrating. Okay, now another statement of the third law of thermodynamics is that the entropy at zero temperature goes to zero. The reason that this is a less satisfactory statement of the third law is that it's not always completely true. Systems can end up with residual entropy at zero temperature. What does that mean? Well, the book goes into one example, and I'm just going to mention it again here. This is actually one of the problems you'll be doing on the homework as well. Take carbon monoxide and freeze it and lower its temperature. So solid carbon monoxide, in solid carbon monoxide, the molecules will tend to arrange themselves in one of two different ways, either oxygen on the left, carbon on the right, or carbon on the left, oxygen on the right. Now, when you drop to absolute zero, whatever way round each molecule finds itself, it can't get out of that state. Right? There's no energy left over at absolute zero for any of these molecules to flip their orientation. But it's completely random what the sequence of orientations are that the solid will end up in. Right? You're going to end up with a completely random set of orientations that the solid is stuck in. But there are many, many ways of arranging these molecules in a random series of orientations. And this problem is identical to the problem of coin flipping. One of these states is heads, one of these states is tails, and it's like flipping an Avogadro's number of coins. The entropy associated with this is equal to the log of the number of microstates, which is the number of ways of obtaining roughly half heads, half tails. In this case, the number of ways that the solid can freeze such that you have about half of them oriented OC and the other half oriented C to O. So obviously that's a finite number. The entropy is finite even at absolute zero. And you can use the statistics you've already examined for coin flips to actually calculate that residual entropy